So, in this chapter, we'll define the first one is the electric potential. Actually, if you have learned the circuit analysis, it is nothing but voltage. But actually, from the physics point of view, it is a little bit different because when you learn the circuit analysis, it regards the physical structure as a lump circuit. So it will be simpler. It drops out all the difficult stuff for the physics, and the rest of stuff is VI, RLC, something like that. And other important variable is the electric potential energy. Other are something related to these two variables. So first of all, electric potential. It is V, and it is defined by this. Suppose you have a rod with positive charge, and you place a test charge Q0 near this rod. So you, for chapter 21, you know that there is some repelling force between them. So this rod will try to push this away, and this one also try to push this away, but this one is much heavier than the charge. So you don't really feel that this one is pushed away, but actually you can really feel this one is pushed away. So you need to have some work to put this charge near the rod. Actually, the work done is like this. You can imagine if this charge is placed infinitely far away, then there is no force, and you can regard it as no potential energy. And as you place close to the wall, you need to pay some energy so that this charge can be placed near the rod or the electric field generated by this rod. And the electric potential is defined by minus W infinity divided by Q0. Q0 is the charge of this particle. And actually, W infinity is the work done by the electric force, not done by you. You can use some work to put the charge near the rod, but actually you can regard it as the electric field doing the negative work so that the charge is placed near the rod. There has a negative difference, but this is very annoying. But actually, when you learn physics, you need to make it clear. And actually, this is the work done by the electric field, and U will be the electric potential energy. So they have a -1 factor between them, and so this equation will be V equals U over Q0. So you can multiply Q to the left-hand side, so it becomes U equals QV. Well, nothing special, I think. Okay, in this slide, so as I mentioned, if a particle is placed near the rod, for different distance, the force are different. So it's similar like that. You can imagine like this. Suppose this is a curvature and you have a ball. You try to push it to the top. Actually, this is quite similar. This is a mass, and you try to push the ball to the top. So if you go upper, if this ball go upper, you will have more potential energy. This is what you learn for physics 1, I suppose. And the potential energy will be mgh, of course. This is something like this. And for this case, if the curvature is like this, and you put the ball here, So initially, we will have some initial potential energy, something like mgh. And at the beginning, it is stopped at the beginning. So it has zero kinetic energy, which is half of mv squared. Okay. So if you just release it, it will try to go down, roll down until here. Then at the lowest pace, final. The potential energy will be 0 because you can regard this is 0, this is h, something like that. Then you will have some kind of kinetic energy, 1/2 mv squared, something like that. It is so-called conservation of mechanical energy if there are no loss, because practically if this ball roll down, it will have some friction force with this surface so that it will roll down, it will ram down and until it will stop here. But if there are no friction in this process, so the mechanical energy is conserved. And so we come back to here. As you see, the potential energy and the voltage has a relationship like this. So if you try to change the potential energy, which means that the voltage or the electric potential is also different. When you go from Vi to Vf, you need to change the potential, the electric potential energy, so that the particle can move from Vi to Vf. Actually, the work done by the electric force is negative delta U. It's negative of this part. So only a minus sign is had here. And as I mentioned, the conservation of energy. So delta K would be this term, actually this line. So this will be the conservation of energy. So the delta K will be minus delta U plus the work applied. Later. So you need some work done so that the potential energy will change, but actually it is equal to the total kinetic energy change. So this is written like this. Okay, so for this sample problem, electrons are continually being knocked out of air molecule in the atmosphere by cosmic ray particle coming from the space.
once release one electron with experience an electrostatic force due to the electric field. Maybe I recap in Chinese. 电子被那个些一些高能的射线被打走啊，因为太空里面有很多那种 gamma ray 那种东西，它打在那个气体的分子上面的时候，那些电子就会被撞走。Okay, once release, each electron experience electrostatic force due to the electric field E that is produced in the atmosphere by charged particle already on Earth. 它就会被打走的时候，它就会产生一些电场。Near Earth surface, the electric field has a magnitude E equals 150 Newton per coulomb and is directly downward. Assume the electric field is like this. What is the change delta U in electropotential energy of a released electron when the electrostatic force causes it to move vertically upward through the distance d equals 520 meter through. So what potential change does the electron move? So actually, it's mentioned that there will be a uniform E field pointing downward, and when the electron was knocked out from the air molecules, so it moved in the E field, so that there is some work done on it, and it asks you when it moves for D, what is the potential change? Okay. So actually, W is F dot D. This is what you should have learned in physics 1, I suppose. The force inner product with the displacement vector, which is the force, which is the work done. So the force will be QE dot D. So this one is what you learned in chapter 22. And as you see, E and D are in opposite direction. So E dot D should be minus QED. So we put in all the values. Minus 1.6 times 10 to minus 19 times E is 150 times 520. So it will be nothing but 1.2 times 10 to minus 14 joule. Or you can return it as 120 femtojoule. So delta U will be minus W. well, okay, this one here, maybe here should have another negative sign because an electron is a negative charge. I forgot this one here. This one, the Q should be negative, and here is another negative sign, so this is positive here. And here should be minus 1.2, 120 femto GeV. So finally, delta V would be delta U 12啊，12才对哦。哦，对 femto 是15 femto 是15。Okay, delta V would be delta U over Q. So Q is again minus 1.6 times 10 to minus 19. So the final answer will be 45 kilovolt. Kilovolt. So any questions up till now? Up till now, quite easy, right? But there will be some monster math coming in this chapter. QED 跟 QV6是符合的。
对啊，就是一点乘地。
哦，对，一点乘地，所以要小心一下。这是一点乘地，是一样的。Okay, the next will be the equal potential surface. So actually, if you try to imagine what is equal potential surface, you can imagine when you look at the Google map or you look at the map, you show maybe circle, something like that, many contours actually, and the contour means that all the points on that contour have the same height. So you can see which is higher, where is lower. And that is similar to the equal potential surface, but it is in 3 dimensions. So here, the adjacent point that have the same electric potential form an equal potential surface, which can be either an imagined surface or a real physical surface. So you can see here, this surface is V1, the second surface is V2, V3, and V4.
On the same surface, all of the electric potential are all V1, and for this one, all of them are V2, so on. Figure of family of equal potential surface. The work done by the electric field on a charged particle as the particle moves from one end to the other end of the path 1 is 0, which means that if a particle is moved from this dot to here, there are no work done, as long as they are on the same equal potential surface. So as path 2. Path 2 is here to here. It actually leaves V3 and go back to V3 again. But actually it do some positive work done and negative work done, so that it go back and the total work done is 0. As long as the initial point and the final point are on the same equal potential surface, the work done will be 0. But for path 3 and path 4, they are not. Actually, the work done for path 3 and path 4 are the same. They move from V1 to V2. So they have the same work done, although for path 4, it goes through V2 and go back. But as long as they have the same initial point, or the initial point have the same electric potential, and the final point also have the same electric potential. So the work done from this point to this point and from this point to this point are the same. Yeah, this is what we mentioned, path 3 and path 4. It's not 0, but has the same value for both these paths because the initial and the final potential are identical for two paths.
So this is the definition for the electric potential difference.
So actually, from suppose a charge Q0 is moved from I to F, the initial to the final position. The electric potential difference, Vf minus Vi. Actually, you can define the electric potential at this point and this point also. So when you subtract them, Vf minus Vi, it will be look like this. This is an line integral. I'm not sure whether you have learned it in the math. Actually, it is a general case for one-dimension integral. Suppose when you learn calculus for one dimension, maybe in x direction, you have something like this. From A to B. So it's just like this is f of x. From A to B, you calculate this area, right? So for the line integral, suppose in well, maybe two dimension. So you have a field. It can be electric field, magnetic field, force field, or any other field. Maybe E in two dimension. E x in I in x direction and y no. So it is a two-dimension if you assume. So maybe you can integrate this
field from any path you like. Maybe I can call it C from initial point to the final point. So actually, it is nothing but you try to E dot ds from I to j. So it will just look like at this point E. So for example, to know the, for example, the E at this point. So you look like E at this point, and ds will be a vector like this. Actually, if you integrate from I to j, the vector will follow this line and going this way. Maybe I use another color. So you just go from this to that. And actually, at this point, ds will be something like this. And at this point, ds will be like this, and this point, ds is like this. It follows the contour, not really necessary to be a contour. Just follow the line you want to integrate. And actually, similar to before, actually you just do all the inner product for the small element, and then you add all of them together. This is the math, but I just try to let you know the physical meaning of this crazy notation. This crazy notation is like this, but actually you do separation and summation. So the voltage difference can be written like this. If you define Vi to be 0, just like what you did in the circuit analysis, usually you define one of the node to be ground, something like that, so that for your calculation it will be simpler. It doesn't really matter whether it is 0, 1, or 100, but as long as you as long as you can define, you can try to define it as 0, so that this one can be simplified like this. And actually, if for this case, if it is only in one dimension, and the field is uniform, so delta V will be minus E times delta X. Yeah, if an integral just integrate a constant, so it's simply as a multiplication, something like this. And the SI unit for electric field can also be written as V over M, because SI unit for voltage is V, of course, and delta X is meter. So you divide meter on both sides. So this one can also be volt per meter. And remember, this one is inner product. So if E and ds is perpendicular, it will be 0. So let's have another example. So for this one, 2 point I and F in uniform electric field. Uniform electric field E. The point lies on the same electric field line and are separated by distance d. So this is d. Find the potential difference VF and VF minus VI by moving the positive test charge Q0 from I to F. This is the test charge Q0 along the path shown, which is parallel to the field direction. Find the potential difference. Okay, find the potential difference. So actually, it's very simple. Vf minus Vi equals minus E minus I to F E dot ds. So actually, E is pointing downward and ds is also pointing downward because it is moving from this place. Too many green, so I change to red. So it moved from I to F. So ds is always pointing downward. So E and ds are in the same direction. So it is nothing but minus IF E ds and minus ed because the distance is d. Distance is d and okay, up to now very simple, right? Any questions? 上一页。哦，So I think if they are not in the same direction, you may consider cosine theta. But I think we assume they are in the same direction. Okay. B. Okay. Now find the potential difference. Again, by moving the positive charge from Q0. The positive charge Q0 from I to F along the path ICF. I is here, C is here, F is here. Okay. So first we try to calculate VC minus VI first, and it will be nothing but this. So for the first half, ds is in this direction, and df, E is pointing downward as the previous page. So E dot ds is 0. So this is 0, 0. Then we try to calculate Vf minus Vi, which will be C to F E dot ds. C. So, for this case, ds is pointing this way with a 45 degree. So it will be E ds cosine 45 degree. Maybe I put it CF here. Actually, the distance it moved will be, maybe I just brush this. So for this one, this is 45 degree, this is right angle. So the distance it moved is actually square root of 2 times d. Right? Because this is also 45 degree. This is d, no matter how you calculate. Using the trigonometry function, using the Pythagoras theorem, it will be square root of 2 times d. So it will be nothing but e times square root 2, so square root of 2 times d, and cosine 45 degree is square root of 2 over 2. So it will be minus ed. And finally, Vf minus Vi. You just need to add them together. This one and this one. So it will be minus Ed. And done. Actually, for these two cases, they are the same. So actually, for these two questions, the initial point and the final point can be regarded as the same. So no matter which path it goes, the potential difference are the same. When you learn the engineering math, the calculus, you will define a term called conservative field. 守恒长. So it has the same property as this one, and actually the E field is one of the conservative field. So any questions? Okay, very good timing, and then we can have a 15 minutes break for the first time and try the calculate.